In this video, we will be discussing the concepts behind stoichiometric calculations. Just as a quick review about how we can symbolically represent various types of reactions, we can represent reactions in terms of the attachment of spheres to form molecules. So in this reaction, we have the O2 molecule reacting with H2 molecules to form water molecules. So we clearly have a rearrangement of how the atoms are attached. If we count up the number of each of the types of spheres on both sides of the arrow, we can see that this is a balanced chemical reaction. There are two oxygens on the left side, two of the red spheres, and there are two red spheres on the right side, whereas there are also then four of the hydrogen atoms. The hydrogens are the green or slightly blue spheres. And on the product side, there are also four of those spheres in the water molecules. Now, we can then change how we represent that in terms of chemical formulas, where we represent the atomic symbol and have subscripts to indicate how many of the atoms are present. So in this case, we have an oxygen, an O2 molecule in the gas phase reacting with two diatomic hydrogen molecules to form two water molecules in the gas phase. And we see here that if we take into account the subscripts in the formulas and the stoichiometric coefficients, we also have a balanced chemical reaction. Furthermore, this can be represented, the stoichiometric coefficients or the multiplication factors can represent the number of molecules, but they can also represent moles. And so in both cases, we're dealing with balanced chemical reactions in terms of either the molecules or the moles. The final thing that we will then have to relate this to is to the mass ratios for the various compounds involved in the reaction. And we can see here that the calculation of the amount of mass of each of the reactants and products can be determined from the molar mass of each of the compounds. So for example, O2 has a molar mass of 32 because an individual oxygen atom is 16. There are two oxygens in the formula, so 2 times 16 is 32. And the unit there is grams per mole. So multiplying 1 mole time, which is the stoichiometric coefficient, times that mass gives you the 32 grams that we have in front of the O2. The hydrogen, in this case we have 2 moles, and the molar mass of H2 is 2 grams per mole, so the 2 times 2 gives us the 4 grams of elemental hydrogen. So if we were to react 32 grams of elemental oxygen with 4 grams of hydrogen, we would then produce the water, and in this case we would produce 2 moles of water, which 2 times the molar mass of water, which is 18 grams per mole, gives us a total mass of the product being 36. You'll notice that the total mass of 32 plus 4 on the reactant side equals the total mass on the product side. At this point, we need to introduce a term that you need to be familiar with, which is stoichiometry. Stoichiometry is a calculation based upon the ratios in a balanced chemical reaction, and this allows us to calculate the appropriate amount of mass for both the reactants and products, and is calculated from the moles. So it turns out that a balanced chemical reaction will tell us mole ratios between the various species in the reaction. So for example, here we have the balanced reaction reacting elemental oxygen with elemental hydrogen to form water. The mixture, if we combine 1 mole of oxygen with 2 moles of hydrogen, is exactly the right ratio to then end up forming 2 moles of water. So we can use these various ratios to do different types of calculations, and this can represent a conversion factor between these various species. So as we see here, it's possible that if we had 1 mole of oxygen and an excess of hydrogen, then we would end up getting 2 moles of water from the reaction. So our conversion factor there, or ratio, is 2 waters for every 1 mole of O2. However, there are other ratios that can be employed in different kinds of calculations as well. So the ratio between the oxygen and the hydrogen is 1 to 2, and this again could be used in various kinds of calculations. And then the final ratio is a conversion factor between the O2 and the water molecules. And of course, we can always do the inverses to get the ratios for the other combinations. So, as an example, if we ask how many moles of water can be produced from 0.78 moles of O2 if there is an excess of elemental hydrogen, we would start with the given in the problem, which is the 0.78 moles of O2, and we see that we want to use a conversion factor that will go from the O2 to the water, because water is the goal of the question. And you'll notice now at this stage we have moles of O2 in the numerator and in the denominator of the combined calculation. And so we can cancel those. That leaves us with the moles of the water. At this stage, if we did the mathematics, we would take 0.78 times 2 divided by the 1. That gives us a value of 1.56. Since there were only 2 significant digits in the 0.78 moles, there's only going to be 2 significant digits in our final answer. So in this case, then, we would round to 1.6 moles of water. So the crucial concept here in terms of stoichiometry is that we can use these mole ratios to do various conversions. So therefore, if we have mass as a given in a problem, the very first thing we would always want to do is convert that into moles. So as an example, how much oxygen is needed to generate 14 grams of water? So in this particular case, we're going to start with the mass of the water. We will then convert that into the moles of water and using some sort of ratio. And then we'll convert the moles of water into the moles of oxygen, because we're trying to figure out how much of the oxygen we're going to need. And then finally, we will use another conversion to go to the mass of the oxygen. So to do this calculation, we need the molar mass of the water. We can calculate that. We are going to need the mole ratio of between the water and the oxygen that comes from the balanced chemical reaction. And we'll need to know the molar mass of the O2, which we can calculate from its formula. So, the first step. If we start with 14 grams of water as the given from the problem, we can then use the molar mass of the water, which is the sum of an oxygen atom, which is 16 approximately, and 2 hydrogens, both of which are 1 gram per mole. So we add those together, we get a total of 18. And you'll notice that we put the grams of the water in the denominator of this ratio because it will cancel with the grams of water in the given of the 14 grams of water. And then that cancels, leaving us with moles of water. If we solve this at this point, we can come up with the moles of the water. However, okay, that doesn't get us to our goal. So if we use that to do the next step of our calculation, do now the ratio in terms of moles from the balanced reaction, and we put the 2 moles of the water in the denominator of that ratio and the 1 mole of elemental oxygen in the numerator, that will allow us to cancel the moles of water, and then that doing the calculation would give us the moles of O2. But that still doesn't get us to the answer yet because we're trying to get the mass of O2. So we got to do our final step, which then involves taking that moles of O2 and then using the molar mass of O2. And at this stage, you can see that the moles of O2 are going to cancel. And we do the math, we come up with our final answer. Well, our final answer, if we pay attention to our significant digits, we're only going to have 2 sig figs. We don't need to round up, so that is 12 grams of O2. If we look at the same problem, we can simplify doing the math by, rather than dealing with solving the ratios at each of the steps of the calculation, we can simply string those ratios together in the dimensional analysis. So if we start with the 14 grams of water and use our ratio between our molar mass ratio to get to the moles of water, the grams of water would cancel. We then multiply by the molar ratio in the balanced chemical reaction, which is 2 waters for every 1 O2. The moles of water would cancel. And then our final step, where we use the molar mass of O2, the moles of the O2 will cancel. And at this stage, we have arrived at the goal of the question, which is how many grams of O2. And so at this stage we can do our math by multiplying everything in the numerator and dividing by everything that's in the denominator. That gives us 12.4, but there's only 2 significant digits, so again we come up with a final answer of 12 grams of O2. This saves us a little bit of time in terms of not having to solve each stage of the calculation.